All right, going on to video number 2, going to look at some of the equation stuff for simple harmonic motion. And you've already done the pendulum activity, and with the pendulum you could see that if you started with some initial displacement, in this case it'd be an angular displacement called theta, that the pendulum wants to swing back towards center. It eventually swings past center, gets to a new position that's roughly equal to what it had when you initially gave it displacement, and then it repeats the cycle over again. So the angular displacement on either side of vertical should be the same. At least that's what you're supposed to see. If there's some friction in there, if it's a little sticky because you have it too close to the wall, that it might not be perfect. But what we wanted to take a look at was what variables actually affected the period. So we've got a little table going here and doing kind of comparatively, not actually putting any numbers in there, but the amplitude in this case would be the theta. So how much angle am I giving the pendulum when I release it so that it can swing? The mass would just, well, it'd be how many washers that I had on mine, and then length would be just how long the actual string was. Now, what you were supposed to have seen, so hopefully you've already finished that and you're not just clicking through on stuff, but what you're supposed to have seen is that if you increase the amplitude, how far away you pull the pendulum, within reason, there's not much of a difference. So amplitude going up or down, if you do a small angle or a big angle, you end up getting the same T. And it might be some differences. We actually have what's called a small angle approximation, which is that, write that in there, that all the simple harmonic motion stuff works really good for springs, but when it comes to the angles of a pendulum, the farther away from vertical you go, the larger that angle is as it approaches 90 degrees. It starts to break down. In fact, past about 20 degrees, it starts to get a little funky in terms of the calculations. But from what you can measure, it's still pretty close to being the same period. If you're getting something wildly different, there might have been other factors going into that. For the mass, you should have seen that if you put 1, 2, 3, 4 washers, fishing lures, whatever, does not affect it. You get roughly the same period. And you're supposed to. It's supposed to be independent of mass, just like so many other things. If you drop a tennis ball and you calculate how fast it's going when it gets to the ground, as long as air resistance is negligible, we don't need to know what the mass is. So with a pendulum, same thing. So if you increase the length of the pendulum, meaning you made it longer, you should have seen that it took longer for it to go back and forth. So the period increased. And if you decreased the length of it, you should see that it went back and forth really, really rapidly. So there seems to be some sort of connection, not maybe direct, maybe not quite direct, but there is some sort of connection between the length of the pendulum and the period. Now, we can kind of make a rough estimate, which, by the way, I apologize, let's go and write L on the length of the pendulum there. There seems to be some sort of connection where we can say that the period of the pendulum is somehow dependent upon the length of the pendulum. Now, it's not going to be T is equal to L. That's just not the equation. But it's going to be not inverse, not squared, or anything like that. So in reality, the equation, which is born out of calculus and which is comes out of all sorts of substitutions and stuff, the real equation is that the period for a pendulum is equal to 2 pi times the square root of L over g, where g represents that good old friend of ours, the acceleration due to gravity on Earth. Now, unfortunately, that was not a variable that we could test for. I couldn't say, hey, well, what if the gravity is less? Do you think it'll take longer for it to go back and forth? And the answer would be yes. If you were to make the acceleration due to gravity somehow smaller, you'd be dividing by a smaller number, which would give you a bigger answer. It would take longer to go back and forth. So same pendulum with the washers and string. If you went up to the moon, it would take longer for it to go back and forth. But that shouldn't be too big of a surprise because it's the force of gravity that's acting on the pendulum that's actually driving it. So that is the real equation for the period of a pendulum, but we should have been able to back that up with some real world experimentation. Now, what we want to do is take a look at where some of the other equations come into play. If you're taking a look at some of the Khan Academy videos, they jump right into some really deep analysis of the situations, and then just magically pop up with some equations, which unfortunately, without doing some deep calculus, you really do just need to drop the equations down. So take a look at those videos if you would like the very, very longhand version of the answer. But based off of what some of those other videos are, the idea, the big idea for simple harmonic motion is that the acceleration is going to be somehow proportional to negative constant times the displacement. And while we can't see it using no calculus, the idea here is that acceleration is the rate of change of velocity, but velocity is the rate of change of position. So we kind of have this idea where it's the rate of change with respect to time of the rate of change with respect to time of position is essentially some negative version of itself. So you take the rate of change of something twice and you get a negative version of it. That's what we call a second order differential equation. And in calculus, that means if you take the second derivative of something, you get itself back multiplied by a negative constant. And the only equation that we have, the only formulation that we have that works for that is sine and cosine. So x must be sinusoidal. If you don't believe me on that, go look up 1,000 calculus videos on second order differential equations, and hopefully that'll clear it up. But otherwise, we need it to be sinusoidal. The catch is that it could be sine or cosine. So x has to be some multiple of a sine or a cosine. But when you go back to your trigonometry, cosines have to start with the initial value other than 0. Sines start at 0. Well, we said earlier that a simple harmonic motion oscillator has to start with a displacement away from equilibrium so that it can get pulled back in towards equilibrium. So we're going to go with cosine as our default. Now, the equation that I've got in the video down below there is below a cosine graph, and as in some of the Khan Academy videos, the way I have it drawn here, it's going between positive amplitude and negative amplitude. So this point right here would represent maybe all the way to the right for the pendulum. And then when it goes down the graph and it gets to that bottom trough, or the lower peak, that would be all the way to the left. Shortcut on the words there. And it repeats that cycle over and over again. Right, left, right, left. I'm going backwards there, but the time it takes to repeat that cycle is the period, which we call capital T, and from the equilibrium up or the equilibrium down is called the amplitude A. So this is a standard graph for what a simple harmonic motion oscillator would look like. The equation, though, the way we calculate it, gets a little funky. We can say that it's a cosine graph multiplied by the amplitude, which stretches it from being 1 to -1 to A to -A. That makes sense. But what's going on inside of it is the funky part. Sines and cosines, tangent as well, they need an angle in there. So we have to put an angle inside. And, well, time is not an angle. Time is in seconds. So we have to put something inside of there multiplied by time that will give us an angle. And there just happens to be something that if we call it some unknown variable, that when we multiply it by time in seconds, we get a angle, in this case radians. So that variable has to be radians per second. Now, the variable that we've been using that has radians per second is the angular speed. Now, we were careful when we first introduced that to call it angular frequency as well, but then we went right back to calling it angular speed. But angular frequency or angular speed, they mean the same thing. It's some number of radians per second. So inside that cosine, it's technically omega times t. But we never use omega when we're talking about oscillators. Instead, we want to talk about something related to the period. So this is where we have to just define some variables and write down some definitions and some equations. So the period of an oscillator connected motion and time, that's what we're doing with that graph. And it's got to be some sort of cosine, it's got to be in radians, and we just said that has to be omega times t. But where does the omega come from? Now, if you look down at the bottom there, we're going to define angular frequency in the case of simple harmonic motion as 2 pi times the regular frequency. So we need to formally, we did in the previous video mention frequency, but here we need to formally define frequency as 1 divided by the period of the oscillator. And the unit for that is technically per second, because if frequency is 1 over a time, where period is a time, then 1 over time is just 1 over seconds. But we're not going to say that the frequency is something happening is per second. That doesn't work very well. So it's waves per second, it's times per second, it's oscillations per second, cycles per second, whatever it happens to be. For computer purposes, it's calculations per second. We have that a special name, which is the hertz. H-E-R-T-Z, like the rental car company, for some reason. But hertz, capital H, lowercase z, represents the number of times per second that something is happening. So if you see something written down as 25 hertz, that means 25 oscillations per second. If you calculate frequency as being 0.2 hertz, that means 0.2 cycles per second. And you can interchange between frequency and period back and forth. Now, if omega is defined as 2 pi times f, that means that the omega is really 2 pi times 1 over t. Now, if I were to put that into a cosine equation, if I've got that formula that I have above that said a times cosine omega t is the equation for an oscillator, then if I were to plug this in up there, I get x is equal to a times cosine. Technically, we would write 2 pi f times t. That's what pops up on your formula sheet for the AP test. But it's also 2 pi over the period multiplied by t. Now, it seems like an extraneous way to write things out, but if we kind of look back at the picture up above, we want to figure out where something is using this equation. The only reason to have that cosine equation is to be able to calculate what the position of an oscillator is. Where is it on its path? So let's go ahead and put in a time that's equal to the period and see what happens. So what if t is equal to the period? Let's go ahead and plug it in and see what we get. We'd have x equals a times cosine of 2 pi over the period times the period. Lo and behold, the t cancels out there for period, and we're left with x equals a times the cosine of 2 pi. And what's a cosine of 2 pi? It's 1. So this is just saying that x equals a at time is equal to the period. So when the time hits that special number called the period, and it goes over and comes back to its original position at that exact amount of time, it's at a position A. That is the magnitude of its displacement. Now, depending on where you start, if you start at positive A or negative A, you have to change what that amplitude variable is, but that is a nice little check to make sure that we're not making like crazy equations.